So in this video, we are going to explore the idea of complexity, computational complexity. We are going to see what is P, what is NP, what is NP complete, and what do all these terms mean, because it's a very big debate in computer science as far as I've heard, and it will be really interesting to get to know these concepts, because then you can seem very cool at a cocktail party or when amongst a bunch of computer science noobs, when you claim that I know what P versus NP is. Yeah, it's a very difficult problem, etc., etc. I'm not implying in any way that I do this, but I may be. So anyway, we're going to first understand the idea of complexity. We're going to see what is P, what is NP. We're going to see what are reductions, and therefore what is completeness. By that I mean, what is this C stands for, what this C stands for in NP complete. What does that complete mean? And so then we're going to look at some strategies, at least talk about them on a higher level, strategies of solving NP complete problems. We are not going to solve these problems. We're not going to prove that P equals to NP, but we will show some way to do NP problems faster than brute force search. Anyway, I'm getting ahead of myself, and I'm going to mention a few examples of NP complete problems, and we'll look at one such examples, or in fact two such examples, in another video, in the next video. So what is complexity? What does that mean? Big O of something. This big O of some garbage here. This tells me how hard or easy a particular problem is, right? I mean, for example, this problem is big O of n square means if I double my inputs, for example, if I give an array of 10 and then I give an array of 20, my time taken to solve this problem, time taken, or let's say resources or whatever, is going to get multiplied 4 times. So doubling the input size results in a 4 times increase, right? Big O of n log n, doubling the input size results in 2 log 2 times increase. So not 2 log 2 times, it's like it will be 2n log 2n divided by n log n. So twice of log 2 plus log n divided by log n. So this depends on what n was initially. I'm just writing this. If I was at n equals to some number, doubling that input size results in this much increase in my time, this much. So as n goes higher and higher, n log n is such an important number for sorting, etc., because as n increases, and even if you double the size of the array, your time taken gets doubled on a very approximate sense, because 1 upon n tends to 0 as n is big. For example, a 1 million array sorting and a 2 million array sorting. If this takes, let's say, x seconds, this will take 2x plus some epsilon. This will take 2x plus some epsilon error, and this epsilon error will be like very small. So anyway, this was just the idea of what complexity is, what complexity means. So what does P mean? the class P. So what is classes mean? What do I mean by this class? Class is just an abstract idea of how I am trying to, put them in. I'm just trying to put a label on problems. So the class, for example, I mean, it's a very abstract idea. You were in, when I was in school, I was in 10th A, and there was a 10th B, and there was a 10th section C. So all these are just classes. These are just abstract ideas which do not exist in the real sense, So anyway, what the class P is just a label. P means any problem that can be solved in O n to the K, where K is any number. Any number. It can't be negative. I mean, it's understood like a polynomial sort of thing. K may be, a million, for example. For bubble sort, K is 2. Like it's a big O of n square problem. Even for any sort of sorting, O of n log n is equals to O of n square. I mean, not equals to, but it's definitely lesser than big O of n square. So I can write O of n log n as O of n square. So anyway, sorting is an O of n square problem. Matrix multiplication is an O of n cube problem, right? It's a polynomial problem because K is 3. Well, if you know stress and matrix multiplication, it's n square log n. But anyway, it's still O of n cube. So K may be a million, 100,000, but it's still a polynomial time solvable problem. That's what P is. P is polynomial solvable. So, well, when I'm asking you what is NP, I'm sure the first thing that comes to your mind is not polynomial. It might be correct to some sense. It is correct because not polynomial. What intuition do you get when you think of not polynomial? It's exponential, maybe 2 raised to n, e raised to n, n raised to n sort of problems. That is indeed correct, but this is not the correct explanation. This is not the correct full form, so to speak, of NP. NP means non-deterministic polynomial. So what does this mean? This, whatever we are talking about on these papers, these are always built around the concept of deterministic Turing machines, right? That is Turing machines which are deterministic in nature, but there is an abstract concept of a non-deterministic Turing machine. So what Turing machines is just a very brief overview, because I'm not an expert on this subject as well. This is something that I have to study. A Turing machine is an infinite tape with something written on this, and then there is a pointer, so to speak, and this will give it some instruction to do. And what this instruction basically is: do something, move right, do something, move left, do something, move right, do something, move left. That's it. And you can, in theory, simulate anything on a Turing machine. That is the point of computer science. I mean, that's indeed how our computers work too, on a very broad sense, because it's just instructions on RAM. Yeah, it's just each and every computer you have is just instructions written on RAM, and those instructions are fed into some CPU, and those zeros, ones turn out to be software. They come together in a sense, and they give you software on your screen when you see that Windows logo pop up, or that macOS logo pop up. But anyway, it's a concept of Turing machine. But non-deterministic Turing machine means non-deterministic Turing machines. What they mean is it's just a way to non-deterministic Turing machines. I'll get back to my thought in a second. Non-deterministic Turing machines, they do not have a determined set of outputs for a particular input. They can I mean, it's a function. It's not something like do something, do right, do something, go left, do something, go right, do something, go left. It's a function of states, so it's not determinable. I mean, it could be anything, and this is just an abstract concept which was made, as far as I can tell, to be able to do brute force search in polynomial time. So polynomial, this is just the high level idea that I understand of non-deterministic Turing machines in polynomial time. Again, I don't have much idea of this, and I'm also very, very beginner in this, and I'm trying to get to learn just in a way of teaching. So non-deterministic Turing machine by definition will solve all problems in polynomial time. If it's solvable in polynomial time on a deterministic Turing machine, I'm sure it can be solved in polynomial time in a non-deterministic Turing machines, because non-deterministic Turing machines are made to do brute force searching, right? So that's that. So what a very interesting thing from this is that every problem in P is also a problem in NP, because if it's solvable in polynomial time in a deterministic Turing machine, it can be solved in polynomial time in a non-deterministic Turing machine too. But then there are very interesting class of problems which are not solvable in polynomial time, right? Those are the NP problems, non-deterministic polynomial time problems. Let's not think about it that much. Just understand that NP problems are hard. They're exponential sort of. Now, what is completeness? Completeness. What does NP complete mean? What is completeness? So before I get to completeness, I'm going to talk about what is reductions. Because NPC, completeness, but before I can get to completeness, I have to talk about reductions. So for example, I have a problem X and I have a problem Y, right? I don't know any solution for problem X, but I know a solution for problem Y. If X can be computed in polynomial time given solution to Y, X can be reduced to Y. See, it's a very straightforward concept. I give you Y, I give you a solution to Y, and all you have to do is do some polynomial computations to get to solution of X. So if X can be computed in polynomial time given solution to Y, X can be reduced to Y, right? So every time when you are presented with a new problem, whenever you're presented with a new problem, you have to always think of reductions. That's what computer scientists tell us, that think of reductions. Is it just another problem for which I know the solution disguised in some polynomial wrapper? So whenever I give you a problem X, you have to think hard. Okay, can I reduce it to some solvable problem Y? Can I reduce it to merge sort, or can I reduce it to any other sorting problem? Can I reduce it to the minimum cut of a graph? And if that is reducible to minimum cut, all I need is the solution to minimum cut, and then I can get to X in a polynomial time, right? That's what reduction means. So now, given this idea of reduction, how are we going to get to completeness? So here's number 3. We talked about P, we talked about NP, non-deterministic polynomial. We are on NPC, we are on completeness. But before we get to completeness, we understood reductions. Reductions is just reducing this problem to a smaller or a problem to which I know the answer, right? And then now we get to completeness. Now a problem can be complete in a class. So I can say that this problem is P complete, or I can say this problem is NP complete. Oh, it comes up again. But let's say I have a complexity class C, right? Just some C. It's a set of problems. And now I want to check for a problem, let's say given alpha. This is a problem that I have. There are two conditions that I will check. If alpha belongs to C, and if all problems in C can be reduced to alpha, right? Everything in C reduces to alpha, which means that if I give you a solution to alpha, you can compute every other problem in C in polynomial time, right? So essentially what this means is that this alpha may be the hardest problem to solve in the entire set C, because given alpha, I can do everything else in polynomial time. Given alpha, I can do everything else in polynomial time. So alpha is actually the hardest problem to solve. If I can get a very strong, very fast solution to alpha, all I need to do is just a polynomial wrapper on alpha, and then I have the solution to entire set C. So that's what NP completeness means. So let's get to it. And of all NP problems, if I have a problem alpha such that given solution to alpha, I can compute all NP problems in polynomial time. That's what NP completeness means. This in no ways is a claim that, I can do NP problems in polynomial time. It's given a solution to alpha. If I have an API that I can call, given a solution to alpha, API of, let's say, problem alpha, I can take any other NP problem, call this API a polynomial number of times and do some clever juggling around, and I can get to solution of my problem in polynomial time. That's what NP completeness means. So an example of NP completeness is, let's say, 3-sat problem, 3 satisfiability problem, the vertex cover, which is, or let's say the traveling salesman problem. We're going to discuss the traveling salesman and vertex cover. But I mean, 3 satisfiability is like saying, given 3 variables, I have to satisfy conditions of 3. So x and y and z and a and not b or c and so forth. I mean, you can give me a million conditions and all of them have to be true. All of them are of 3 variables and all of them have to be true, and therefore there must be a solution. There must be one ideal solution or many or multiple ideal solutions such that all of these conditions are true. And this is an NP complete problem. Vertex cover problem is something like, if I have a graph, let's say this one. If I have a graph, then I have to choose the minimum possible minimum set of vertices such that those set of vertices cover every edge possible. So what that means is, for example, in this graph, if I pick vertex A, then the only edge that A has included is this edge, which I'm going to highlight in green, is this edge. But if I take the vertex B, then all of these edges have been included. So if I go to any arbitrary graph, you can see how this is going to turn out to be a difficult problem. I have to pick the minimum possible vertices such that all of the edges, so to speak, are included in such a way that they are incident on one of these vertices. And I can feel this intuition how this vertex cover and 3-sat problems are very closely linked. So for example, if I call these vertices A, B, C, D, E, F, G, H, I, then vertex cover problems is either take A and then not take C and then take D, then and take C and not A and not B, and so forth. So for all three combinations of vertices, you can form a condition, and satisfying that condition will result in a minimum cardinality subset of vertex that will be the vertex cover and also the 3-sat. Now traveling salesman problem is something similar. Given a densely connected graph, I mean, I'm emphasizing densely connected. It's like saying that you are a salesman on the world, and you have some cities to visit, and all cities are connected to each other. You have to do a tour, like go from 1 to 2 to 3 to 4 to 5 to 6. I mean, take an entire visit each and every city exactly once, return to your original city with the minimum cost. So going to 1 to 3 to 4 to 5 to 6, 1 to 3 to 4 to 5 and then back to 1 takes the minimum cost, and not going from 1 to 3 to 4, 1 and going to 3 and then going to 2 and then going to 5 and then going to 4 and then going to 1. That is more than something else. And that, so finding this ideal tour is the traveling salesman problem, which is also an NP complete problem. So we're going to discuss about these problems in detail. But anyway, that's what NP completeness means, that every other problem in NP can be reduced to these forms. That given a traveling salesman problem solution, given an API to solve traveling salesman problem, I can solve any other NP problem. That's why it's NP complete. So if you want to prove that a problem is really, really hard, try, if you want to, sometime prove that this problem is interactable. How do you prove that a problem is interactable? If you are able to prove that that problem is NP complete, then you're golden. I mean, you have overwhelming proof that it is the hardest problem, so to speak, in the NP universe. That if I were to solve this NP complete problem, then I can solve every other NP problem, including other NP complete problems too, because that's also a part of set. So if I have a problem, let's say beta, and if I can show that any other NP complete problem can be reduced to beta, then beta is an NP complete problem, right? Because see, I can reduce an NP complete problem to beta, which means I can reduce every other problem to NP complete problem and then can reduce to beta. That means I can reduce every other problem in NP to NP complete to a problem beta. So if I want to prove that beta is NP complete, if I take another NP complete problem and reduce it to beta, then I can then that's proof that beta is NP complete, because every other problem can be reduced to beta indirectly, so to speak. This is a polynomial time operation, this is a polynomial time operation, so combined it's a polynomial time operation. So beta is NP complete. So that's a way to prove that this problem is really hard. So here then there's this P versus NP debate, where the only question is P equal to NP? That's it. That's the only question. Is P equal to NP? And if that's the case, then all of our cryptographic algorithms will break down. But anyway, if that's the case, then that would mean that NP problems are solvable in polynomial time. That is indeed the question that has $1 million of prize. $1 million if you can prove this. And Kurt Gödel says that it is possible, but also Gödel's incompleteness theorem says that this might be true, but you can't prove it, because that's just how every system is. Every mathematical system every complete system is that it's incomplete, so to speak. That's what Gödel's incompleteness theorem is. It might be true, but you just can't prove it. And Gödel hypothesized that P is equal to NP, but he also hypothesized that you might not be able to solve it. So it's a difficult problem, to say the least. So now let's get into some strategies. Let's get away from abstract concepts. I know they're very fascinating, at least to me, but let's go into some strategies of solving NP complete problems. So the first strategy is focus on special cases. So what do I mean by special cases? For example, two-sat problem. Two satisfiability, just take A and B and take B or C and so forth. I mean, just two variables instead of three. It's a special case. It is solvable in polynomial time. 3 sat is NPC. So we will look into how a special case problem can be solved. Second is heuristics. Heuristics means fast but might not be correct. Might not be, correct. And third, brute force still. I mean, do not brute force, to so to speak. Design an algorithm design. It's not polynomial, but still faster than brute force, right? So focus on either special cases, like take 2SAT, or focus on special cases and try to build a solution from there. Either focus on heuristics, they're fast but they might not be correct, do some processing after that. And third is algorithm design such that they are not polynomial for sure, because it can't be unless P equals to NP. This I have to say, they're not polynomial, but they're still faster than brute force search. And this is something that we're going to investigate in the very next video, which is going to be about the traveling salesman problem. So again, the strategies to solving NP complete problem, the one we are going to focus on is algorithm design such that they are not polynomial but still faster than brute force search. Also, vertex cover problem falls into this. Vertex cover solution that I have studied falls into this particular case. So in the next video we are going to talk about the traveling salesman problem. For now, this I know was a very abstract and very over the top video, but it's very interesting to me, and I want to be able to prove this. So what we studied today, what we understood today was the complexity, P and P complete reductions, and we looked at some strategies of solving NP complete problems. Polynomial time problems, that's what P means. Not non-deterministic polynomial, or let's say not polynomial time problem, that's what NP means. Non-deterministic, they are polynomial on non-deterministic Turing machines, which I think are constructed to be able to do brute force searching in polynomial time. So hence by definition they will be polynomial time problems. We know P, the class P, is a subset of NP. So every problem in P is also an NP problem, because NP is non-deterministic polynomial solvable problem. Reduction, if X can be computed in polynomial type given solution to Y. I give you an API for Y, and you call that API a polynomial number of times, and you can calculate the answer to X. So X can be reduced to Y. Let's just solve Y, and X is in your hand in polynomial time. So complete, a problem can be this set C complete if it falls in that set C, and every other problem in C can be reduced to alpha. So that's what NP completeness means. NP completeness means that every other NP problem, non-deterministic polynomial problem, can be solved in polynomial time given a solution to this particular NP complete problem. So 3-SAT, vertex covered, traveling salesman problem, all of these are NP complete problems. They are also, you know, in polynomial time reducible to each other, because that's what the definition of NP completeness means. So you need to be able to see some similarity, some sort of high level pattern in all of these three. They should be similar in some sense, because I have some intuition on how 3-SAT and vertex cover are just two sides of the same coin, and therefore all other NP complete problems are too. They should be reducible to one another in polynomial time, and given a polynomial solution to this, if you were to be able to find a polynomial solution to NP complete problem, you have a polynomial solution to NP complete, and on top of that, given a polynomial time, you can calculate every other NP problem, and therefore you have proved that P equals to NP. So all you need to do in order to prove that P equals to NP is find a solution to a NP complete problem that is polynomial time. That's it. Now think about how hard NP complete problems are, that if you are able to find just one, you can get. I mean, the entire computer science and the entire computer scientist forum is on this debate whether P is equals to NP or not. God Gödel says P might be equal to NP, and I am a very big Gödel fan, so let's see. And yeah, strategies to solve NP complete problems. Let's try to come up with those strategies without looking at the paper. Number one will be focus on special cases, such that 2-SAT for solving the 3-SAT problem. Some processing might be required, but focus on special cases. Number 2 will be heuristics. They are fast, but they may not be correct. Number 3 is still algorithm designing, which is dynamic programming, or something else which is greedy, or dynamic programming, or anything else which is not polynomial time, but it's still faster than brute forcing. So those are the 3 strategies: special cases, heuristics, better than brute forcing, special cases, heuristics, and better than brute forcing. So in the next video, we're going to look at the traveling salesman problem, and a very neat algorithm, and how I'll motivate the idea of that algorithm step by step. And we're going to solve a traveling salesman problem not in polynomial time, but better than brute forcing time. So the third strategy, that's what we are going to follow for traveling salesman.